All right, let's dive into one of the weirdest quirks in chemistry. We're going to talk about a situation where the normal rules of separating liquids just break down. A point where two different liquids get so comfortable with each other, they flat out refuse to be pulled apart. We are talking about azeotropes. And to really get our heads around this, let's start with a really practical puzzle. You've probably heard this before. If you have a mix of ethanol and water, why can't a simple distillation process ever get you to 100% pure alcohol? The answer to that question is exactly what we're going to uncover today. So here's our game plan. First, we're going to build a perfect, ideal model of how things should work. Then we'll throw in the messy reality of how molecules actually interact, and that's going to lead us to a really cool logical puzzle. Once we solve it, we'll finally define what this thing is and talk about why it's so important. Okay, let's get into it. To really understand why some mixtures behave so strangely, we have to start with how they're supposed to behave in a perfect theoretical world. And this perfect world is described by something called Raoult's law. Just think of vapor pressure as how badly a liquid wants to escape and become a gas. Raoult's law basically says that for an ideal mix, the total desire to escape is just a simple straight-line average between the two pure liquids. It's clean, it's predictable, it's a perfect straight line. And this is fantastic for separation, right? Because in this ideal world, the vapor that boils off is always a little bit richer in the more volatile stuff, the stuff that escapes easier. So you can just boil, condense, repeat, and with every single step, you get a purer and purer substance. Easy peasy. But you knew there was a but coming, didn't you? The real world is just not that simple. In reality, molecules don't ignore each other. They push, they pull, they interact, and all those little interactions completely mess up our perfect straight line. These interactions create what we call deviations. So if the molecules kind of repel each other, they're practically pushing each other out into the vapor phase. That gives you a higher pressure than you'd expect. That's a positive deviation. But if they're attracted to each other, they want to stick together in the liquid, which leads to a lower pressure. That's a negative deviation. Our nice straight line now has a bulge or a sag. Now, a lot of times, these are just little gentle curves, no big deal. But for some mixtures, think chloroform and acetone, the molecules really like each other. The attraction is so strong that it's not just a little bend anymore. It's a massive plunge. And this is where things start to get really weird. So let's head to that tipping point. We're about to run into a fascinating logical puzzle that, well, nature itself had to figure out how to solve. Okay, let's do a quick thought experiment. Imagine we take that negative deviation, that sag in the pressure curve, and we just keep pushing it down. Let's exaggerate it, make it more and more extreme. What would that phase diagram even have to look like? You'd be tempted to draw something like what you see here. You've got your liquid up top, gas on the bottom, but hang on, take a close look at that lowest red area. What we've drawn implies that you can have a gas with one composition sitting right next to a gas with a different composition, and they're somehow in equilibrium. So I have to ask you, does that make any sense at all? Physically, can you really have two different gases coexisting like that, not mixing? No way, right? Of course not. We know that if you put two gases in the same container, they're going to diffuse and mix almost instantly until they form one single uniform gas. You can't have two separate gas phases in equilibrium. It just doesn't happen. So the diagram we drew is physically impossible. So how does nature solve this puzzle? It's actually really elegant. Since that gas-gas region can't exist, the diagram has to fix itself. The liquid curve is forced to dip all the way down and touch the gas curve at its lowest point. They meet at one single specific composition. And right there, at that one magic spot, the composition of the liquid is exactly the same as the composition of the vapor boiling off of it. This special point, this clever little workaround to a logical paradox, it actually has a name. We've just figured out why azeotropes have to exist. So, an azeotrope is a mixture that, at a very specific ratio, basically pretends to be a pure substance when it boils. The vapor that comes off it has the exact same makeup as the liquid. There's no separation happening, no enrichment of one liquid over the other. It is a distillation dead end. And these things come in two main flavors, which tie right back to those deviations we talked about earlier. You can have minimum boiling azeotropes, which come from those strong positive deviations, and maximum boiling ones, which come from the strong negative deviations we just worked through. A minimum boiling azeotrope happens when the molecules repel each other, that positive deviation. Since they're pushing each other away, it takes less energy, a lower temperature, to get them to escape into a vapor. This means the mixture actually boils at a temperature lower than either of the pure liquids on their own. And the maximum boiling type is the total opposite. This comes from that strong attraction between molecules. Because they're holding onto each other so tightly, you have to pump in more energy to break them apart. This means the mixture boils at a temperature that's even higher than either of the pure components. So that's the theory. We've walked through the logic. But why is this so critical in the real world? Let's bring it all back home to our starting question. The reason this all matters, as the source material says so clearly, comes down to one single crucial process: distillation. Understanding azeotropes is everything when it comes to knowing if you can actually separate a mixture or not. So let's put all the pieces together. The way water and ethanol molecules interact causes them to form a minimum boiling azeotrope at about 95.6% alcohol. And at that specific point, the vapor that boils off has the exact same 95.6% composition. Since distillation only works by separating different compositions, the whole process just hits a wall. You literally can't get any purer using a simple still. You are stuck. And that leaves us with one last big question. We know it's possible to buy 100% pure ethanol, so simple distillation can't be the end of the story. What comes next? What kind of clever chemical engineering tricks, like adding a third chemical or messing with the pressure, are used to break that azeotrope and get past the 95% barrier? Now that is a whole other fascinating story.